Thank you so much, and good evening, everyone, or good afternoon in Korea. And let me start off by apologizing for my voice. Unfortunately, I came down with a cold today, so please let me know if I say something that isn't understandable, and I'll repeat myself. But today, I'm really excited to tell you a little bit more about what we're working on at C0. Of course, throughout this forum, we've heard a lot about the need to decarbonize and the importance of hydrogen. And I want to talk a little bit more about the way we are doing that. We are pursuing that at C0. So to begin, I won't spend too much time on this because I think we are all well aware, but carbon dioxide emissions are driving climate change. You see significant increases in CO2 levels globally, and commensurate with that, we also see significant rises in temperature, in global average temperature, compared to the middle of the 20th century. So I think we're all aware that we need to significantly reduce CO2 emissions, and that one way to do that is by increasing the adoption of hydrogen as a fuel. And this is really because hydrogen is a potential solution to several different decarbonization needs. So you can use hydrogen for vehicle transportation. You can use hydrogen for synthetic fuels, for upgrading oil and biomass. We use a lot of hydrogen already for ammonia production and fertilizer production. We just heard how you could also use ammonia as a hydrogen carrier. So we have existing need for hydrogen and ammonia, and that might be increasing in the future. In the metals and refining industries, they're looking at replacing some of their existing carbon-based reduction processes with hydrogen. You can replace natural gas heating with hydrogen heating. And one area that we're particularly interested in at C0 is replacing natural gas combined cycle turbines with hydrogen combined cycle turbines, or even simple cycle turbines if the demand and interest arise for that. And while hydrogen may not be the solution for every challenge at every location, we think it's undeniable that will play a critical and lasting part in the decarbonization of the future. So when people think about hydrogen sources, where do you get your hydrogen from? I think people usually think of two main ways. The first is conventional hydrogen generation through what's often called gray hydrogen, or hydrogen from a process called steam methane reforming and water gas shift. And this is a process where you take natural gas and you take water and you produce hydrogen, but you also unfortunately produce quite a bit of CO2. The other process that I believe a lot of people are familiar with is electrolysis, where you take water and electricity and then you split the water into hydrogen and oxygen. The challenge here is that electrolysis requires a significant amount of energy. What I'm showing here in this slide is the thermodynamic requirements, or the requirements for these processes at 100% efficiency. And you see that with electrolysis, you require at minimum about 40 megawatt hours per ton of hydrogen produced. So it's a significant amount of electricity that's required to produce hydrogen from water. In contrast, we're really interested in another process called methane pyrolysis, where we're taking the natural gas and we're producing hydrogen from it directly without CO2 emissions. So how does that work? Well, to start, we have to step back and talk about a misconception that we often see, which is that CO2 is the only byproduct of hydrocarbon energy. And that's not the case at all. In fact, when you take natural gas and you use it for energy, you produce twice as much water as you do CO2. So what C0 asks is, what if we could access just the energy in the hydrogen and leave the energy in the carbon behind? When you look at the total amount of energy in natural gas, 60% of it comes from the hydrogen and 40% comes from the carbon. When we look at, say, total US energy production, you see that 60% of existing natural gas production in the United States would be 20 quadrillion BTUs, or about 20% of total energy production, 5 times current wind and solar here in the United States. When you look at Korea, and you see the total amount of natural gas consumed in Korea, it's about 1.6 quadrillion BTUs. Converting that to hydrogen with methane pyrolysis would produce about a quadrillion BTUs, or about 10% of all of Korea's energy requirements. So it's an absolutely massive opportunity here in the United States and in Korea. It's also important to note that when we start with renewable natural gas or natural gas that started off as biomass, this process goes from being carbon neutral to being carbon negative, where we're taking CO2 from the atmosphere, we're sequestering it in the form of biomass and renewable natural gas, and then separating out that carbon and hydrogen to produce carbon negative energy. So that's really the mission of C0, which is to provide low cost, low emission energy from natural gas. We do that by producing hydrogen, but from a really big picture standpoint, what we care about is tackling that natural gas challenge. Natural gas is a huge and vital energy source in the world, and we need to significantly reduce its CO2 emissions as we move to a decarbonized future. And here what you can see are all of the potential markets that hydrogen can help play a role in. So it's not just hydrogen's current market, it's also electricity, transportation, process heat, and more. So just a little bit about the company. We were founded in 2018. We're located in California. The work really starts back in 2016 when our CTO, Professor Eric McFarland, started researching this at his lab before we decided to take it to commercialization. Since then, we've raised about $50 million with some amazing investor base. And in particular, I want to thank SK Gas, who are our most recent investors and have been an amazing source of not just financial support, but also technical support. And one thing that we really are impressed with at C0 is the seriousness and the dedication that SK Gas is showing to creating a hydrogen economy. So that is something that we are very impressed with, and one of the main reasons why we were so excited to have SK Gas join us in this mission. And we're still a small company with a growing patent portfolio. So here you can see just a picture of the team. It's led by our CTO, Professor Eric McFarland, who I mentioned briefly. He's got quite a bit of experience commercializing technologies like a gas to liquids technology in the 2000s, an organic solvent process in the 2010s. We've got some great people like our VP of engineering, Steve Calderon, that's piloted many different hydrocarbon processes. We've got experts with over 100 years of experience scaling up challenging chemical engineering processes and several PhDs, including myself, from places like MIT, Caltech, Imperial College of London, and UC Berkeley. So just a quick slide here on our facilities and capabilities, which of course are, for a 20-person company, significant, but for a university, still rather small. And luckily for us, we are located right next to the University of California, Santa Barbara, and we are able to leverage their resources as well. But we have several walk-in fume hoods where we can test and pilot systems. We've got ability to cut metal, to machine prototypes, to test rapidly. We've got spectroscopy, microscopy, and elemental analysis tools like scanning electron microscopes and XRFs in order to analyze what we are producing and to look at things like corrosion and materials of construction, able to do extensive process modeling and design of our processes as well. One sec, please. So what is our process? How do we go about splitting methane into carbon and hydrogen? Well, we do this using a high temperature liquid. So what we're essentially doing is we take natural gas and we bubble it in a high temperature, multi-phase, multi-component melt system. And this melt system splits the methane into carbon and hydrogen. And then we're able to take that carbon and fluidize it out with the hydrogen and separate that out with conventional solid gas separation processes, primarily cyclone filtration. And what makes us unique compared to other entities that are looking at methane pyrolysis or have looked at methane pyrolysis is that we're the first to really be focused 100% on hydrogen production. We are focused on the hydrogen aspect and not on the carbon because the hydrogen / energy markets significantly dwarf all carbon markets that don't go to energy use. So essentially, that dwarf all carbon markets outside of coal and coke. Just to give you a sense of that, if you take just 10% of the existing hydrogen market today, convert that to methane pyrolysis, you would swamp all carbon markets outside of coal and met coke. And that's not including all of the future uses for hydrogen that we've heard about throughout this day. So it's an absolutely massive opportunity, but we cannot rely on existing carbon markets as end uses and end cases for the carbon that we're producing. And instead, what we're focused on is making the lowest cost, lowest emission hydrogen possible. And one of our key differentiators there is energy efficiency. If you recall at the beginning, I talked about how electrolysis requires quite a bit of energy to split water into hydrogen and oxygen. It requires about 40 megawatt hours thermodynamically. In real life, it requires usually north of 50. In contrast, methane pyrolysis requires 86% less energy than electrolysis per unit of hydrogen produced. But that's if you're careful and if you're close to the thermodynamic minimum for methane pyrolysis. So we believe that maintaining that differential is going to be critical as we scale up this technology. Now, here's just a very simple video from one of an old experiment that we have that just allows you to see this occurring in real life. So what we're doing here is we're bubbling methane into a high temperature molten system. That methane is being split into solid carbon and hydrogen. And then that hydrogen and carbon are leaving the reactor and are being separated out by these cyclones. And so you can see the carbon is being filtered here at the bottom, and the hydrogen is going to the end use that you want to use the hydrogen for. And what's important here to note is that the carbon that you're seeing here is carbon that was originally in the methane. This is carbon that would have been converted into CO2 had we not done this process right now. So it's a very visible way in which you can decarbonize your natural gas. This is a method of natural gas decarbonization where you're producing a solid where the carbon accounting is very simple and very straightforward. You can credibly take that mass of carbon and say, this mass of carbon would have been CO2 had I let it combust in, let's say, a turbine, but instead I am removing it and then I'm using the product hydrogen instead, producing no direct CO2 emissions. So here's a high level schematic of the process, where what we're doing is we're taking 1 gigajoule of natural gas. So it's about 1 million BTU. We need some amount of energy. As I mentioned, it's still a process that requires energy. We need about 0.2 gigajoules of heat for every gigajoule of natural gas. And then we produce 5 kilograms of hydrogen and 15 kilograms of solid carbon. It's important to note here that 15 kilograms of solid carbon are equivalent to 55 kilograms of CO2, because CO2 is only 27% by mass carbon. The rest is really oxygen. So CO2 sequestration is really oxygen sequestration. And this can be thought of as a more pure version of CO2 sequestration or carbon sequestration. The other thing I want to talk about is the fact that unlike water splitting or electrolysis, we have the ability to provide the energy for this reaction from different energy sources. So we need heat, but that heat could come from anywhere from natural gas to hydrogen to electric heating. So those are all options that we have at our disposal, and all ways that we can actually provide the heat depending on the customer, depending on their needs, depending on what they are looking for. So of course, if you're using natural gas to heat this process, you will produce some amount of CO2, but the amount of CO2 that you'd produce would still be a 75% reduction compared to existing steam methane reforming processes. So it'd still be a significant reduction in CO2 intensity. However, If a customer is not interested in that and would rather burn some of the product heat as a product hydrogen or use electricity as heat, we can do that as well. So that optionality, we think, will be very relevant as we talk to customers at different locations in different countries with different regulations. Those all will play a factor into which one of these sources of heat we will use to drive their reaction. So where are we today? Well, at C0, we're working with world-class EPC firms to build our first pilot. That we hope to have online. We plan to have online the first quarter of 2023. And the main focus for this pilot is really demonstrating the scalability of this process, where we're going from the lab. If you recall the video or the images that I showed you earlier of our lab in Santa Barbara, where you're only able to build essentially test stands that can produce maybe 10 kilograms of hydrogen a day, to processes where we're able to produce 400 kilograms of hydrogen a day at pressure. And it's, of course, important to note that anytime you're producing 400 kilograms of hydrogen a day with methane pyrolysis, you are by definition also producing 1,200 kilograms of carbon a day. Because even though 60% of the energy in natural gas is in the hydrogen, 75% of the mass is in the carbon. So when you are doing this process, when you are doing methane pyrolysis, you are producing more carbon by mass, 3 times more carbon by mass than hydrogen every single time. And so managing that carbon, managing the carbon removal, managing the carbon handling is actually some of the more challenging aspects of methane pyrolysis. We like to say that actually producing the hydrogen is easy. It's the production of the carbon and the transporting of the carbon away from the reactor and storing it or sequestering it safely, which is the significant challenge for all methane pyrolysis processes. It's also important for us to be able to demonstrate this at pressure. So this process, this pilot that we're working on, will be operated up to 10 bar of pressure. And the reason for that is because we think, for economic reasons, where you don't want to pay for the compression cost of the hydrogen, and you also don't want to pay for the added volume for your reactor, this process really needs to operate at pressure. So those are some of the main things that we're working on with this first pilot that you see here. We are also working right now to design our second pilot, which will be an order of magnitude larger in throughput, so 10 times larger in throughput than this first pilot. And that one is going to be the one that we really hope it shows the commercial readiness and the commercial, essentially it will be the first commercial unit for our process. So we don't think that this pilot unit that we're building right now is of a commercially viable scale, but we think the next one that we're building will be. And that's the one that I'm showing right here. So again, as I mentioned, we're first working on our pilot for Q1 of 2023. And then soon thereafter, we will begin developing and building out our second pilot, which we hope to be fabricating in 2024. And that one will produce at least 10 times more hydrogen than the previous one. And that's really what we believe is the minimum viable scale for our hydrogen process. So we don't see this as being something that is viable for, say, 50 kilograms of hydrogen a day or 100 kilograms of hydrogen a day. We really see this as being a process that's best suited for several thousand kilograms of hydrogen a day, up to hundreds of thousands of kilograms of hydrogen a day. And we also think this is critically important because in order for this to really make an impact on reduction of CO2 emissions worldwide, it needs to be scalable. When you think about the amount of hydrogen necessary to even decarbonize a single combined cycle turbine in Korea, you are talking about a methane pyrolysis or a hydrogen generation facility that is producing several 100,000 tons a year of hydrogen just for that single turbine. And so for that reason, all of these hydrogen processes, hydrogen generation processes, need to be scalable. They need to be processes that can really work and operate at scale that are commensurate with conventional, traditional steam methane reforming processes. So that's one of our biggest focuses as a company, making sure that we're not producing any process that, or working on a process that does not scale. And we're helped and assisted with by this with world-class EPC firms and pilot plant developers who have many, many years of experience working on these kinds of systems. I also want to touch briefly about a common question we get, which is, what do you do with all of the carbon that you produce? So as I mentioned, existing carbon markets are not large enough to absorb all of this carbon. So we think there are two different possibilities. In our base case, what we think is this process should be economically viable if what we are doing is sequestering the solid carbon. So you can think of the carbon sequestration as an alternative to CO2 sequestration. And in geographies and locations like Korea and like parts of California, where you simply cannot do CO2 sequestration, carbon sequestration is a significantly simpler way to sequester your carbon, where what you're doing is you're picking up a solid byproduct and you're just sequestering it, like we sequester so many things globally. And here, what we're showing is actually the amount of carbon that you would produce from methane pyrolysis in contrast to wind and solar production. So when you look at producing 1 terawatt hour of electricity over 30 years, you would need over 900 acres of wind to produce that amount of electricity. Now, with that, you can still likely use the land for other uses, but not so for solar. And for solar, you would need over 100 acres to produce a terawatt hour over 30 years. In contrast, the amount of carbon that we'd produce would fit in a cube that's 47 meters in length. And so while it might sound like a lot of carbon, in reality, we will always have some sort of waste product from zero emission electrical generation, whether that is CO2 in the form of CO2 sequestration, or solid carbon from methane pyrolysis, or even decommissioning solar panels at the end of their life. There's just no getting around the fact that all of these processes will produce some amount of waste. Now, with all of that said, we are also looking at potential uses for the solid carbon. And we are specifically interested in potential uses for the solid carbon that are markets large enough that can absorb the amounts of carbon that we're discussing. So it's not existing carbon markets that we have today, but could this solid carbon be a positive when added to soil? So a soil amendment-like material, that is something that we are exploring. Could the carbon be used in cement or in asphalt to improve their stability, to improve their mechanical integrity? That's something that we're exploring. Could the carbon be used as a low-grade activated carbon alternative, where what you're doing is actually using it to do remediation, site remediation, where you're using it in places where you have landfills, and what you want to do is prevent leaching of different materials in your landfill? That's something that we're also looking into. So just to give you a sense, those are the kind of scales of carbon markets that are interesting for us. Unfortunately, as much as we'd like to, the carbon markets for things like batteries or carbon nanotubes or carbon fiber are just orders of magnitude too small to be really commensurate with the amount of carbon that we'd produce if we were successful at C0. And so while it's interesting to study those carbon applications, they're likely not going to be long-term solutions for our carbon. So I'd just like to summarize. C0, our process, really unlocks the zero emission potential of natural gas. We think of it as pre-combustion carbon capture. So instead of producing CO2 and then having to sequester it and transport it potentially, we simply remove the carbon from the natural gas before it is produced. We also believe that solid carbon is superior to CO2 for several reasons. It's significantly denser than uncompressed CO2, unsurprisingly, because it is a solid, not a gas. It's lighter than the equivalent amount of CO2 because it doesn't have any oxygen along with it. It's easily transportable. Anywhere where you've built infrastructure, you know by definition that you can get solid mass to that site and that you can get solid mass out of that site. So it makes it much cleaner. You don't have to worry about potential geography challenges. You don't have to worry about building a new pipeline. We already know how to move solid mass around. And it can be sequestered anywhere. You don't have to worry about geological formations. And where we are right now is we're moving to pilot with an experienced scale-up team with some great partners, investors, collaborators, including SK Gas, who have been truly wonderful to work with. And with that, I'd like to thank you so much for your time. And of course, happy to answer any questions you might have. And apologize again for my voice if it sounds too hoarse. Thank you.